This video explores the topic of sensor fusion within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Today we will explore how modern intelligent systems combine data from multiple sensors to achieve reliable perception, robust estimation, and smarter decision-making. As measurement systems evolve toward digital, connected, and autonomous platforms, sensor fusion becomes essential for reducing uncertainty and improving system performance. In this session, we move beyond the basics and focus on advanced filtering, probabilistic models, system architectures, and AI-driven fusion. We will look at how classical approaches, such as Kalman, extended Kalman, and particle filters, integrate with modern machine learning methods to build powerful hybrid fusion pipelines. Real-world examples from autonomous vehicles, UAVs, industrial automation, IoT, and biomedical monitoring will illustrate how these techniques support the goals of PEMS-ML and modern measurement science. By the end, you will have a clearer picture of how advanced fusion improves accuracy, resilience, and intelligence across diverse applications. The quote, "A single sensor can tell you what's happening, but multiple fused sensors can tell you why," perfectly captures the motivation behind sensor fusion. The idea is straightforward. Every sensor has limitations: noise, drift, blind spots, or delays. But when we combine multiple complementary sensors, we can significantly reduce uncertainty and obtain a much more accurate understanding of the system or environment. Sensor fusion allows us to merge strengths and compensate for weaknesses, ultimately producing estimates that are more reliable than anything a single sensor could deliver. This is why fusion is fundamental in modern intelligence systems, from autonomous vehicles and drones to industrial automation, smart devices, and medical monitoring. It enables better decisions, higher precision, and improved robustness, which are essential for safety-critical and high-performance applications. Sensor fusion is a core enabler of modern intelligent systems because it combines the strengths of multiple sensors to create a far more accurate and reliable understanding of the environment. In autonomous vehicles, fusing camera, LiDAR, radar, and GPS data produces a robust world model that supports safe navigation, even in challenging conditions. Drones and mobile robots rely on the fusion of IMU, magnetometer, GPS, and vision to maintain stable flight and precise localization, allowing them to operate even when one sensor becomes unreliable, such as temporary GPS loss. In industrial automation, merging information from temperature, pressure, vibration, and vision systems improves process control and early fault detection. Everyday devices like smartphones and wearables also depend on fusion, combining accelerometer, gyroscope, and magnetometer signals for orientation, or heart rate and motion data for accurate activity and health monitoring. The key advantage across all these domains is enhanced accuracy, robustness, and redundancy. Fusion reduces noise, resolves sensor weaknesses, and ensures systems can still function under sensor failures or harsh conditions. Ultimately, it provides the complete situational awareness required for reliable, real-time decision-making in fast and dynamic environments. This slide introduces one of the simplest yet most fundamental sensor fusion methods, weighted averaging based on sensor noise. When two sensors measure the same physical quantity, but each has different noise characteristics, the optimal fused estimate is obtained by weighting each measurement inversely to its variance. In other words, sensors with lower noise contribute more to the final estimate, while noisier sensors contribute less. The formula shown expresses this idea mathematically. If x1 and x2 are the sensor readings, and sigma 1 squared and sigma 2 squared are their noise variances, the fused value is a weighted combination where each measurement is scaled, as it is shown in equation 1. The fused variance is also reduced compared to either sensor alone, reflecting improved confidence. This is essentially the same principle used in the best linear unbiased estimator and represents the static version of a Kalman update. This method is optimal when sensor noise statistics are known and when we're performing a single-step fusion without system dynamics. Typical applications include redundant thermometers, distance sensors, industrial probes, and simple robotic or environmental monitoring systems. Even though it's a basic technique, it forms the conceptual foundation for more advanced filters, such as the Kalman filter, which extends this idea into dynamic recursive estimation. The complementary filter fuses two sensors by exploiting their different frequency characteristics. One sensor is filtered with a low-pass filter to capture long-term stability, while the other is filtered with a high-pass filter to capture fast dynamics. When we add these filtered signals, we obtain a fused estimate that combines the long-term accuracy of one sensor with the rapid responsiveness of the other. A common example is IMU, orientation estimation. The accelerometer provides a long-term tilt reference but is noisy during motion, whereas the gyroscope gives smooth, short-term angular information but drifts over time. The complementary filter blends these two using the following weighted update. Here, alpha is typically between 0.95 and 0.99, meaning we trust the gyroscope more for rapid motion, while the small term 1 minus alpha uses the accelerometer to slowly correct drift. This formulation is computationally extremely efficient, making it ideal for real-time embedded systems. Because of this balance between accuracy and speed, complementary filtering is widely used in drones, smartphones, wearables, and embedded robotic platforms that require fast and stable orientation estimation. Time synchronization is one of the most important practical requirements in sensor fusion. Because sensors operate at different sampling rates, IMU at 100 Hz, camera at 30 Hz, GPS at 5 Hz, their measurements refer to different moments in time. If we fuse them without aligning timestamps, we introduce inconsistencies that can lead to false object detections, incorrect positions, or unstable navigation. To avoid this, systems rely on shared hardware clocks, precise timestamps, buffering of fast sensor streams, and interpolation of slower ones so all data correspond to the same time instant. In robotics, for example, IMU data are timestamped. Camera frames are buffered until matching IMU times are available, and GPS is interpolated between updates. When perfect synchronization isn't possible, tools like RAWS message synchronizers and Kalman filters that estimate time offsets help reduce errors. The key idea: reliable fusion requires reliable timing. Without proper alignment, even the best algorithms will fail. All sensors have imperfections, and understanding these errors is crucial for effective fusion. Sensors generate random noise, often modeled as Gaussian, along with systematic errors such as bias, scale factor distortion, and temperature-dependent drift. Over time, some sensors, like gyroscopes or wheel encoders, experience drift, while others suffer from latency caused by communication or processing delays. Environmental factors such as lighting, magnetic disturbances, or temperature shifts can further degrade measurements. To handle these issues, fusion algorithms model uncertainty explicitly. Each measurement is assigned a variance, and the fusion process naturally weights sensors by inverse uncertainty, giving more trust to stable, low-noise sources. A classic example is combining an encoder, which has low noise but drifts, with GPS, which is noisy but drift-free. Together, they yield a position estimate that is both stable and accurate. This highlights why proper modeling of noise, bias, drift, and uncertainty is essential for reliable sensor fusion. Sensor fusion relies on probabilistic methods to combine noisy, uncertain measurements into a single reliable estimate. Bayesian filters like the Kalman filter, EKF, UKF, and particle filters explicitly model process and measurement noise, allowing the system to optimally weigh each sensor. With multiple sensors, redundancy becomes a powerful tool. Outliers or faulty readings can be detected and rejected using techniques such as RANSAC, thresholding, or Mahalanobis distance. Good fusion performance also depends on calibration. Estimating and compensating biases, offsets, or scale errors in sensors keeps the fused estimate accurate over time. In many real systems, noise levels change, so adaptive filters adjust the covariance matrices QQQ and RRR on the fly. For example, increasing RRR when a camera becomes unreliable. Finally, pre-processing steps like low-pass, high-pass, or band-pass filtering help remove known noise patterns before fusion. Together, these methods ensure robust, stable fusion even in challenging, real-world environments. Bayesian filtering provides the foundational mathematical framework behind most modern sensor fusion systems. The central idea is that we never observe the true system state directly. We only get noisy measurements. So the filter uses Bayes' theorem to continually estimate the hidden state, by combining what we already believe with what the sensors just observed. This happens through a repeated predict-update cycle. In the prediction step, we use a motion or process model to forecast the next state. In the update step, we correct that forecast using the new sensor measurement following the key relationship. Depending on the problem, different filter families apply. The Kalman filter is optimal when everything is linear and Gaussian. For nonlinear systems, we use the extended or unscented Kalman filter, and for highly complex or multimodal distributions, particle filters provide a flexible, sampling-based alternative. Overall, Bayesian filtering is powerful because it not only fuses sensor data, but also tracks uncertainty explicitly, making it ideal for real-time navigation, robotics, autonomous systems, and any application where decisions must be made under uncertainty. The Kalman filter is the fundamental linear Bayesian filter used when both the system dynamics and the measurement process can be modeled as linear with Gaussian noise. We describe the system with two equations: a state equation, shown in equation 4, which predicts how the state evolves, and a measurement equation, as it is shown in equation 5, which links the hidden state to what our sensors observe. Both process noise W and measurement noise versus are assumed to be Gaussian with covariances Q and R. The filter maintains a belief about the current state as a Gaussian distribution shown in equation 7, where x to the power of k is the best estimate and pk represents its uncertainty. Each cycle, the Kalman filter performs a predict step, computing as shown in equation 8 and projecting the covariance forward, and then an update step, where the Kalman gain kk determines how much to trust the new measurement compared to the prediction. A high Kalman gain means the filter relies more on the measurement. A low gain means it trusts the model more. Overall, the Kalman filter provides an optimal weighted fusion of prediction and measurement, making it extremely powerful for real-time tracking, navigation, and control in systems where linear Gaussian assumptions hold. The Kalman filter provides smooth and reliable state estimates by intelligently combining past predictions with new sensor measurements. Instead of reacting directly to noisy data, it balances memory and new information, producing stable results even when measurements fluctuate. As the filter runs, the Kalman gain naturally settles, meaning it learns how trustworthy each sensor is and automatically adjusts how much influence new data should have. A major advantage is resilience to missing or delayed measurements. If a sensor drops out, such as GPS failing in a tunnel, the filter continues predicting, with uncertainty growing gradually, and then corrects itself as soon as the data returns. Each update step can be viewed as an inverse variance weighted average, where precise sensors contribute more strongly than noisy ones. For linear systems with Gaussian noise, the Kalman filter is mathematically optimal, delivering the lowest possible estimation error, while maintaining robustness during real-world operation. The extended Kalman filter is used when our system or measurement models are nonlinear, which is common in robotics, navigation, and sensor fusion tasks. Unlike the standard Kalman filter, which only works for linear systems, the EKF handles nonlinear dynamics by linearizing the system around the current estimate. We start from nonlinear functions for state evolution and measurement, as shown in equation 10. At every step, we compute the Jacobians partial differential f/partial differential x and partial differential h/partial differential x, which act as locally linear approximations of the models. These matrices are then plugged into the standard Kalman prediction and update equations. In essence, the EKF performs a first-order Taylor expansion around the current state estimate, enabling approximate Bayesian filtering even when the true system is nonlinear. This approach is computationally efficient and widely used in applications such as GPS/INS fusion, converting radar or LiDAR measurements to Cartesian coordinates, robotic localization, and smartphone motion tracking. However, because the EKF depends heavily on linearization quality, it can become inaccurate or even diverge if the system is highly nonlinear or if the initial estimate is poor. The unscented Kalman filter is designed to address one of the main limitations of the extended Kalman filter, the need for linearization. Instead of approximating a nonlinear system with Jacobians, the UKF uses the unscented transform, which propagates a carefully chosen set of sample points, called sigma points, through the nonlinear functions. These sigma points are deterministic and preserve the mean and covariance of the original state distribution, allowing the filter to capture nonlinear behavior much more accurately. In the prediction step, each sigma point is passed through the nonlinear motion model according to equation 11, after which the predicted mean and covariance are reconstructed from their transformed values. The same idea is applied in the update step. The sigma points are passed through the measurement model H-dot operator, forming predicted measurements and measurement covariance, and the update proceeds similarly to a standard Kalman filter but without Jacobians. The main advantage is that the UKF is significantly more accurate for systems with strong nonlinearities and avoids the sensitivity of the EKF to poor linearization or difficult derivative calculations. Because of this, UKF is widely used in UAV and ground vehicle navigation, IMU quaternion fusion, radar and LiDAR tracking, and many other nonlinear state space applications. A particle filter is a powerful approach for sensor fusion when systems are highly nonlinear or when the uncertainty cannot be represented well with a single Gaussian distribution. Instead of maintaining just a mean and covariance, the particle filter represents the belief using a cloud of many weighted samples, or particles. Each particle is a possible state of the system. During prediction, every particle is propagated through the nonlinear motion model. When a new measurement arrives, each particle is assigned a weight based on how well it explains that measurement. This is the likelihood. The particles with higher weights represent more plausible states. To prevent the set from collapsing, a resampling step is applied so that highly weighted particles are duplicated and low-weight ones are removed. The result is a very flexible posterior distribution that can represent multiple hypotheses, sharp nonlinearities, and even multimodal beliefs, capabilities that linear filters like KF or EKF cannot offer. Particle filters are widely used in Monte Carlo localization, SLAM, and target tracking, where ambiguity or non-Gaussian noise is common. The main limitation is computational cost. As the dimensionality of the state grows, the number of required particles increases rapidly. But when accuracy under complex scenarios matters, particle filters remain one of the most versatile tools in advanced sensor fusion. In sensor fusion system design, the architecture you choose has a huge impact on performance, scalability, and robustness. In a centralized fusion setup, all raw sensor data is streamed to a single processing unit. This gives you the most complete information and often the highest quality estimates, but it also demands significant bandwidth and creates a single point of failure. In contrast, decentralized fusion divides the workload. Each sensor or subsystem performs local processing, and only intermediate results are sent upward. This structure reduces communication load, improves fault isolation, and is widely used in robotics and automotive platforms where different modules operate semi-independently. Finally, distributed fusion removes the central unit entirely. All agents or nodes share information peer-to-peer and collectively converge to a fused estimate. This approach is extremely robust and well-suited for multi-robot teams, sensor networks, and large IoT environments, but it requires more complex algorithms and careful handling of communication delays. Overall, choosing the right fusion architecture means balancing information richness with scalability, reliability, and computational constraints. When we talk about fusion levels, we are essentially deciding at what stage different sensor streams are combined, and each level offers a different balance between information richness, complexity, and robustness. Data-level fusion merges raw signals directly, like combining IMU readings, LiDAR point clouds, or stereo camera images. This approach preserves the most information, but it also demands high bandwidth, perfect time synchronization, and strong computational resources. Feature-level fusion works on extracted features instead of raw data, such as key points, detected objects, or tracked features. This reduces data volume and allows each sensor to use its optimal preprocessing method, but it inevitably discards some raw information. Finally, decision-level fusion merges the final outputs of subsystems, such as object classifications or event detections. It's simple, modular, and easy to integrate across heterogeneous sensors, but it keeps the least amount of detail. In practice, early fusion provides the highest fidelity, while late fusion offers scalability and robustness. Feature-level fusion often represents the best compromise. Architecturally, centralized systems tend to support data-level fusion, whereas decentralized and distributed systems typically rely on feature or decision-level fusion for efficiency and resilience. As sensor fusion systems scale up, several practical challenges must be addressed to maintain reliability and real-time performance. The first critical issue is synchronization. When many sensors operate at different rates and delays, maintaining precise temporal alignment becomes increasingly difficult, and even small timestamp errors can produce incorrect fused estimates. Next is dimensionality and scalability. As the number of sensors or tracked objects grows, the state space expands, increasing computational demands and requiring more efficient filtering or approximation methods. Another challenge is correlated sensor errors, where multiple sensors share the same noise source. If we treat them as independent, we underestimate uncertainty, so methods like covariance intersection are needed for safe fusion. We also need to handle out-of-sequence measurements, which occur frequently in distributed networks, where data may arrive late. Finally, real-time constraints are essential in autonomous systems. Fusion must run within tight deadlines, often under 100 milliseconds, which drives the use of hardware acceleration and pre-filtering. A good example is an autonomous car, where LiDAR, radar, and cameras generate massive data streams that must be fused extremely fast to ensure safe and reliable operation. In modern sensor fusion, deep learning introduces a fundamentally different approach compared to classical probabilistic filters. Instead of manually defining models or deriving Jacobians, data-driven fusion allows neural networks to learn how different sensor modalities should be combined directly from examples. Convolutional networks, recurrent networks, and multimodal architectures can ingest camera images, LiDAR point clouds, radar signals, or IMU streams, and automatically learn the optimal fusion weights. This makes them extremely powerful for highly nonlinear, high-dimensional problems, such as autonomous driving, where camera, LiDAR, radar fusion is now a standard pipeline. Similarly, LSTM-based models can capture temporal dependencies in IMU data and provide robust motion estimates. The key advantage is that these models can represent complex relationships that classical methods struggle with, enabling end-to-end perception or prediction systems. However, they also require large annotated datasets, which can be difficult to interpret, and safety certification remains a challenge. Despite these limitations, AI-driven fusion is rapidly evolving and is increasingly used to complement traditional Kalman-based approaches, especially in applications where rich sensor modalities and nonlinear interactions dominate. In this section, we look at one of the most advanced directions in modern sensor fusion, deep learning-based camera LiDAR integration. The core idea is to use a two-stream neural architecture, where one stream processes camera images using a CNN to extract rich semantic information, such as object appearance, texture, and class. The second stream processes LiDAR point clouds, often with voxel-based or point-based networks, to capture precise 3D geometry and depth. These two complementary representations are then fused either early, by projecting LiDAR features into the image plane for joint feature learning, or late by merging separate detection outputs. This multimodal fusion greatly enhances perception accuracy because cameras excel at semantic understanding, while LiDAR provides reliable range information, especially in low visibility or long-distance scenarios. Such architectures are now widely adopted in autonomous driving systems like NVIDIA Drive, and similar principles extend to visual inertial odometry and IMU vision fusion. Overall, this data-driven approach offers a powerful alternative to traditional probabilistic fusion by learning complex cross-sensor relationships directly from data. In this part, we highlight some of the most important emerging trends in modern sensor fusion. Reinforcement learning-based fusion allows systems to dynamically choose which sensors to trust under changing conditions. For instance, relying more on radar in fog. Federated fusion enables distributed devices to train a shared model without exchanging raw data, which improves privacy and reduces bandwidth. Graph neural networks are increasingly used to model complex relationships across large sensor networks. We also see progress in uncertainty-aware deep models, such as Bayesian neural networks, which provide confidence estimates for safer decision-making. Overall, the field is moving toward hybrid approaches that combine the reliability of classical filters with the flexibility and expressiveness of modern AI techniques. In autonomous vehicles, sensor fusion is essential because no single sensor can provide complete, reliable perception. A modern self-driving car combines cameras, radars, LiDAR, ultrasonic sensors, and GPS plus IMU, creating a redundant and complementary sensor suite. For perception, the system fuses camera, LiDAR, radar data to detect, classify, and track vehicles and pedestrians. Cameras provide rich semantic information, LiDAR provides accurate 3D geometry, and radar contributes precise velocity. Tracking modules, typically based on EKF or UKF, merge these observations over time to maintain stable trajectories even during noise or partial occlusions. For localization, GPS, IMU, wheel odometry, and LiDAR map matching are fused to achieve lane-level accuracy, with IMU bridging GPS dropouts and GPS constraining IMU drift. Similarly, wheel encoders, steering sensors, and IMU are fused to estimate vehicle speed and yaw rate for safe control. Overall, centralized or decentralized fusion architectures ensure real-time performance and provide the redundancy required for functional safety and fault tolerance. In drone systems, sensor fusion is essential for achieving stable, accurate 3D flight in constantly changing environments. Modern UAVs rely on a rich sensor suite that includes an IMU gyroscopes and accelerometers, along with a magnetometer, barometer, GPS, and often optical flow or vision sensors. For attitude estimation, or AHRS, the fusion of gyro, accelerometer, and magnetometer data is critical. The gyro provides fast motion information but drifts over time. The accelerometer provides the gravity direction, and the magnetometer stabilizes heading. Filters such as complementary filters or Kalman-based AHRS combine these signals into reliable roll, pitch, and yaw for the flight controller. Altitude and position estimation also depend on fusion. The EKF integrates barometer data, which is smooth but drifting, with GPS, which gives absolute but noisy measurements, and IMU vertical integration. Indoors or in GPS-challenged environments, optical flow or vision sensors help maintain stability. High-rate IMU updates, often hundreds of hertz, bridge the gaps between slower GPS updates, enabling responsive control during wind gusts or rapid maneuvers. Platforms like PX4 use a 21-state EKF and perform continuous consistency checks, activating fail-safes whenever sensors disagree or degrade. In industrial and robotic systems, sensor fusion is essential for achieving precision, reliability, and safety. Robotic arms combine joint encoders, force torque sensors, and vision to obtain accurate joint states and perform fine manipulation tasks. In quality inspection, fusing camera, laser, and acoustic data reduces false detections and improves defect identification. Mobile robots and AGVs use LiDAR SLAM fused with wheel odometry to maintain robust localization. LiDAR corrects drift, while odometry bridges short gaps. In process industries, temperature, pressure, and flow sensors are fused through Bayesian or Kalman-based methods to estimate hidden variables and detect faulty readings. Collaborative robots also rely on depth cameras and force sensors to detect human presence and enhance safety. Altogether, sensor fusion significantly strengthens precision and operational robustness in Industry 4.0 environments. Sensor fusion significantly improves the accuracy of wearable and medical monitoring by combining signals such as heart rate, motion, respiration, and skin temperature. This multimodal approach provides more reliable detection of activity, stress levels, sleep patterns, and early signs of anomalies like arrhythmias or falls. By integrating multiple biosignals, systems can offer continuous, real-time health insights and reduce false alarms. Fusion also supports personalized medicine, creating individualized health profiles that enable tailored interventions and predictive management of chronic conditions. Overall, fused biosignals make digital health monitoring more precise, robust, and patient-specific. Sensor fusion in smart environments combines both environmental sensors, such as temperature, humidity, air quality, and light, with motion sensors like accelerometers and gyroscopes to build real contextual awareness. By integrating these complementary data streams, systems can accurately interpret user activity, location, and surrounding conditions. This enables smarter automation. HVAC, lighting, and equipment can adapt in real time to occupancy, movement patterns, or environmental changes. In modern IoT ecosystems, multi-sensor fusion allows devices to coordinate more effectively, share context, and operate with higher reliability and energy efficiency. The result is a more intelligent, responsive, and efficient environment that continuously learns from both user behavior and ambient conditions. Environmental monitoring relies on combining multiple sensor sources to create a more accurate and reliable picture of air and weather conditions. Air quality and meteorological sensors, such as PM, nitrogen dioxide, O3, carbon dioxide, temperature, humidity, and wind, are fused to produce consistent environmental assessments that no single sensor can deliver alone. By integrating satellite remote sensing data with ground station measurements, systems achieve higher spatial resolution and better calibration of atmospheric variables. Fused data streams are essential for early warning systems, enabling timely alerts for pollution peaks, wildfires, heat waves, and severe weather events. Modern cloud and edge-based fusion platforms support real-time processing, cleaning, and merging of these diverse data sources, providing robust decision support for environmental agencies, smart city platforms, and public health systems. Future sensor fusion research is moving toward handling high-dimensional data, such as hyperspectral cameras and 4D radar, using more efficient, compressed representations. Another key direction is semantic fusion, where physical sensor measurements are combined with maps, databases, and contextual knowledge to create a richer understanding of the environment. As IoT systems expand, edge and collaborative fusion methods enable devices to share perception and run lightweight algorithms directly on device. Robustness and safety are increasingly important, driving work on fusion techniques that resist adversarial attacks, spoofing, and extreme conditions. Emerging technologies like quantum sensors will demand new models capable of leveraging their unprecedented precision. Finally, the field is pushing towards standardized frameworks that ensure interoperability, synchronization, and reliability across diverse fusion systems. Sensor fusion fundamentally improves measurement quality by reducing uncertainty, increasing robustness, and combining the strengths of multiple sensors, since no single sensor works well in all conditions. The core idea is to start from simple fusion methods like averaging and complementary filters, and then progress to advanced Bayesian approaches such as Kalman, extended/unscented Kalman, and particle filters, selected according to system linearity and noise characteristics. Fusion architecture also matters. Centralized and distributed frameworks, as well as early, feature-level, and decision-level fusion, each bring different trade-offs in bandwidth, scalability, and fault tolerance. Modern systems increasingly integrate AI, where deep learning provides powerful multimodal fusion capabilities, but hybrid AI plus classical filtering remains the most reliable and interpretable solution. Across domains, autonomous vehicles, drones, robotics, IoT, and healthcare, the principle is the same. Combining data sources produces better, more stable estimates than any single sensor alone. Effective engineering requires continuous evaluation of noise, drift, reliability, and failure modes to ensure the fusion pipeline remains trustworthy and resilient. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš, and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.